Hello, good afternoon. I hope I am audible.
Yes, ma'am.
Okay, thank you for confirming. So welcome to the 8-week problem solving session of applications of power electronics in power systems. I shall share my screen. Can you see the presentation?
Yes, ma'am.
Okay, okay. Yeah, so let's start. In last week's discussion, we talked about the different roles of static bar compensator other than voltage control. The primary role is obviously controlling the voltage so that during the when uh, during the phenomena of under voltage or over voltage, it can provide a certain amount of reactive power or it can absorb based on the necessity, and it can maintain the system voltage and prevent it from go from dipping to a very low voltage or rising to a very high voltage, which could be detrimental for the equipments and the overall system. That is its primary role. Other than that, it has other advantages, such as it can increase the steady state power transfer capability of the system, and it can also increase the transient stability margin of the system. And lastly, it can provide damping in case of power system oscillation. Today, the main topic of discussion will be the way how we can control the SVC, how we can control the voltage so that the damping can be provided whenever there is an oscillation in the system. Okay. And we will also solve some numericals on this topic. Yeah. So today what I will do is I will start the problems from the beginning, and while there will be some where will be the explanation is required, I will explain the concepts. So while solving the problems, I will explain the concepts instead of just telling the concepts first and then starting the problems. I think it will be better if we do it in this way. Yeah, so the first question is, if the midpoint voltage of an SVC connected transmission line is maintained constant, then what is the nature of the system? So there is a transmission line and SVC is connected at the midpoint, and we are maintaining the midpoint voltage constant. Then what is the nature of the system? Is it critically damped, or it is underdamped, it is undamped, or it is overdamped? So there are various type of systems. So whenever there is some oscillation, we provide damping so that the oscillation dies down. Suppose this is the steady state value. It may be any quantity, it may be some voltage, current, or any electrical quantity. Suppose there is this oscillation and its amplitude is constant. It continues to oscillate like this, then we call this system undamped system because the oscillations are continuing. It is not dying down. But if the nature of oscillation is like this, suppose this is the steady state value and the oscillation is like this, so the amplitude gradually reduces, then we say there is damping. Okay. And it gradually reduces and eventually it settles down at the steady state value. Then we say there is damping in the system. The system is damped. Now there are there are different kinds of damping. So there may be the system may be critically damped, the system may be under damped, and the system may be over damped. Okay. So you must have studied all this in your basic electrical uh, basic electrical subjects. So yeah, so we have to determine what is the nature of the system if we maintain the midpoint voltage constant where the SVC is connected. Okay. Now suppose now I will just explain how we can get to the answer. So we will start from this system where no SVC is connected. So this is just a transmission line. No SVC is there, only the transmission line. This is the sending end with the voltage V1 angle delta and the receiving end V2 angle 0. So, and the X is the reactance of the transmission line. And we know that this we already studied that this is the steady state power V1 V2 by X sine delta without any compensation. Now, if we consider the swing equation, so this is the inertia constant M del 2 del delta by del D2 plus del P equal to 0. Okay. So sometimes we call this accelerating power also. What is this del P? This is some incremental power, some delta power, change in power. And how we can represent it? We can represent it like this. Del P by del delta multiplied by this perturbation in delta. So if you carefully look at this expression of this power, so V1 and V2, they are usually constant, and for a particular transmission line, this quantity is also constant, the reactance. So the power is basically dependent on delta, the power angle. That's why whenever there is a perturbation in delta, then we will get a perturbation in power also, because the power is dependent on delta. It is a function of delta. Okay. So this is basically the swing equation, and this quantity is very important quantity. This del P by del delta, this one, the which I have put in bracket, this is called the synchronous coefficient. Okay, synchronous coefficient. Suppose Ks, we can denote it by Ks. Okay. Now, when this quantity is positive, when this coefficient is positive, in that case, we get the solutions. We get two solutions which are imaginary. So if you do this, if you solve this in Laplace domain, then you will get a square plus omega n square, where omega n is what? Natural frequency of oscillation. Okay, natural frequency of oscillation. So this is equal to 0, you will get, where omega n is what? Omega n is root over of Ks by m. Okay. What we are doing is basically we are just dividing m here and here. So this is a square plus Ks by m, then is equal to 0. So as solutions, you will get plus minus, if Ks is positive, plus minus j omega n. That's what you will get as the solution. Okay. So they are imaginary. Therefore, whenever we get this kind of solution, the system is marginally stable. Okay. The system is undamped. So the oscillation will go on. This we are considering a lossless system, obviously. So the oscillation will go on. There is no damping in the system. Okay. But for the stability of the system, we need some damping. We can't let the oscillation go on forever. We have to give some damping. And how we can do that, that we will discuss in the next slide or in some later slides. Okay. How we can introduce damping in the system. So this was a typical second order system, undamped second order system. Now we will introduce damping. How? By introducing this SVC. Okay, by introducing this SVC. And this SVC is placed at the midpoint of the transmission line, where the midpoint voltage is Vm and the angle is delta M. Okay. Now, if you see, if we maintain this voltage, this midpoint voltage Vm, if this is constant, suppose, so this is constant, okay. We always maintain this constant irrespective of what is the load, okay, what is the sending in voltage, receiving in voltage. So this is constant. In that case, what is the steady state power? P compensated. Still, mind it, still there is compensation. So SVC is there. The system is compensated system. We are maintaining the voltage, right? So the compensated power will be V2 Vm x by 2 sine delta m. Okay. Now, if this is already a constant and Vm is also a constant, you see again the power is only a function of delta m. Okay, the power is only function of delta m. So you will get the swing equation will remain the same, except that it becomes delta m. This delta is changed to delta m. Otherwise, everything is same. So again, you will get a marginally stable system. And when you get a marginally stable system, the system is undamped. There is no damping. That's why we can't maintain this voltage constant if we want some damping. If we want to damp the oscillations, we can't maintain Vm constant. We will have to vary it. Okay. So we will get back to the question. What was the question? If the midpoint voltage of an SVC connected transmission line is maintained constant, then what is the nature of the system? The system will be undamped because the voltage is constant. Midpoint voltage is constant. Okay. So the next objective is how we will have to somehow vary this voltage. Okay, we will have to somehow vary this voltage, and how we will vary this so that the system gets damped, that we will see. Okay. So suppose now the first case was Vm is constant. The second case is Vm is not constant. Vm is not constant. Okay. Is variable. Suppose this is a variable. Okay. So in that case, the swing equation will change. Okay, the swing equation will change. Why? Because this del P comp will change. Earlier, del P comp was only a function of del time. Okay, this power angle. But now there is another quantity, this Vm, which is also variable. So it needs to be considered. Now this is the expression of del P comp. Del P comp by del Vm and delta Vm, and this was already there, this portion. And now we will express delta Vm in terms of delta del M by delta T. Okay, this like this. So delta Vm we have replaced by this. Why? Because we will now vary this quantity accordingly. As delta M changes, del Vm will also change. As this changes, as this varies, this will also vary. Okay, so this will also vary, and we can express this delta Vm like this, where k is a constant, proportionality constant, and this is the control variable delta M. Sorry, this is not the control variable. This will anyway change, and we will change delta Vm accordingly. And this is the new swing equation. So this part was already there. This part is the additional one that is just introduced when we are varying Vm. So this is the new part, and this part was also there earlier. Now you see this, apart from this and this is the new part. And this part basically introduces the damping. This zeta is the damping coefficient, and omega n is the natural frequency of oscillation. Okay. So this is the new part. And we can express this damping coefficient like this. Okay, this is the damping coefficient. This is omega n, this is omega n, and this is the damping coefficient. So now, this much we understood, that if we vary this midpoint voltage, then we will introduce additional term in the swing equation, which basically provides which is the term that provides damping. Okay, that is the term for damping. So till this point, is it understood? This portion will not come unless we vary the voltage Vm. When we vary the voltage Vm, then only this term comes, which is 2 zeta omega n. Okay, yes. Okay. So now we can proceed to the next problem. A three-phase 400 kV 60 Hz 850 kilometer long symmetrical transmission line operating with Vs equal to Vr equal to 1 per unit and rated load of the line corresponding to delta equal to 60 degree. The line inductance is this 1.5 millihenry per kilometer. Capacitance is 5 nanofarad per kilometer. And SVC is to be placed at the midpoint of the line. The limit of the control range corresponds to delta equal to 40 degree and delta equal to 90 degree. So in between this range, the system will operate. The minimum is 40 degree, maximum is 90 degree. What is the value of the Thevenin voltage corresponding to the rated load? Okay. Now this is some new term. What is the Thevenin voltage? So how how do we get to the Thevenin voltage, and why do we at all require to calculate Thevenin voltage? Now I will explain. Okay, so we discussed that we need to vary the midpoint voltage Vm. We need to vary the voltage at this point to provide damping to the system power system oscillation. Okay. Now, for to do that, what we will do? We will vary this voltage. And what is this voltage? This voltage is and how we will know what voltage is at this point? We will control the voltage at this point, right? And how we will know what is the voltage at this point? We need some generalized expression. And what will be the generalized expression? That is the Thevenin voltage. You know, right, what is Thevenin equivalent circuit? In basic electrical, you must have studied Thevenin, Norton, all these things. Thevenin equivalent. So basically, in a Thevenin equivalent circuit, we determine what is the Thevenin voltage, VTH, and we also determine the Thevenin impedance. Okay, we determine the equivalent Thevenin impedance, ZTH. Okay, and here, okay, so we need to determine the Thevenin voltage and Thevenin impedance at this point, at this midpoint. Okay, at this midpoint. So obviously, what is the Thevenin voltage at midpoint? The midpoint voltage Vm. And what is the expression? This is the expression. V cos delta del by 2 by cos beta L by 2, and the angle is delta by 2. Okay, this is the Thevenin voltage. Just a second. I will just get back in a second. Yeah, so the Thevenin equivalent volt. Uh, yeah, the Thevenin equivalent voltage is this. Next, we need to find out what is ZT, the Thevenin impedance. We know the sending end voltage expression in terms of midpoint voltage and midpoint current. When the eraser is not working. Anyway, yeah. So the sending end voltage we can express in terms of midpoint voltage and midpoint current. Whenever we determine the Thevenin equivalent circuit, the Thevenin for determining the Thevenin equivalent balance impedance, what we need to do is we will short circuit this voltage source, this sending end voltage source. Okay, so that is the way. So whenever you determine a Thevenin equivalent impedance, you just short circuit the this other voltage source. Okay, so Vs equal to 0. You will have to put. In that case, what you will find? You will find Vm by Im, this expression. You will find this expression. Okay. So this is Vm and this current flowing is Im. If you just take the ratio, you will find the Thevenin impedance. Okay. You will find the Thevenin impedance. That is ZC sin beta L by 2 by cos beta L by 2, where ZC is the characteristic impedance. Okay. So this is tan beta L by 2. But this impedance is from sending end till the midpoint. Okay. So this is sending end till midpoint. Similarly, you will get from midpoint to the receiving end the same equivalent impedance. Okay. Thevenin impedance. So the effective Thevenin impedance will be the parallel combination of this. And they are same because the line is symmetrical. So this will be the actually the effective Thevenin impedance, half ZC tan beta L by 2. And if you just apply KVL in this loop, if you apply KVL in this loop, then you will get VSBC equal to V Thevenin minus ISBC XTH. Okay. What is ISBC? ISBC is the current flowing through this SBC, this current. Okay. So now let's solve this question. Yeah, so we need to find out what is the Thevenin voltage, right? So what is the Thevenin voltage? So we just saw the Thevenin voltage is the, I would write it here. Okay. So VTH was V cos delta by 2, delta by 2 by cos beta L by 2, beta L by 2. And the angle we don't have to consider for now. Okay. So what are the informations we have already? We already know delta because they have uh, they have said to consider the rated load at delta equal to 60 degree. So we already know delta. What we need to find? We need to find beta L, right? Now, what is beta L? Beta L is equal to omega root LC multiplied by L. L is the length of the transmission line. So what is omega? Omega is 2 pi. This is the angular frequency, 2 pi times 60, because the frequency is 60 hertz. That is mentioned. And L and C values, they are also mentioned here. L value is 1.5 millihenry and C value is 5 nanofarad. Okay. This is milli and then 5 nanofarad. And then L. What is L? L is 850 kilometer. So this is 850. After this, we will get in radian. Okay. This value will come in radian. So can you please calculate and tell what will be beta L? Just replace all the values and find out what is beta L. Yeah, are you there? Okay, so I will just write the value. The beta L value in radian comes out to be 0.877. And if it is converted to degrees, then it is rad, and in degrees it is 50.28 degree. 50.28 degree. Okay. And we need to find out the answer in per unit. So no need to multiply this V, which is 400 kilovolt, because we are finding out the per unit value. So V Thevenin will be simply cos delta by 2 cos delta by 2 by cos beta L by 2. Cos delta by 2 is cos 30 degree. That is 0.866. And cos beta L by 2 is 0.9 0, 5 to 7. 5 to 7. So the Thevenin voltage is 0.9566 per unit. Okay. So the correct answer is option C, 0.957. Okay, let's go to the next question. What is the Thevenin reactance? So that is also very easy. What is the Thevenin reactance? The Thevenin reactance, ZTH, we can also denote it as XTH because we are talking about reactance. So this is XTH basically. Okay. So XTH will be half ZC 10 beta L by 2. This is the Thevenin equivalent reactance. Okay, this is just the magnitude. Okay, this is just the magnitude. So first, what is required? ZC value, the characteristic impedance value. That is also known to us. Why? Because we know the L and C values. And characteristic impedance is root over L by C. Okay. So this is 1.5 millihenry per kilometer. So this is milli, that would be 10 power minus 3, and here it is 5 nanofarad, so 10 power minus 9. Okay. And if you calculate this, I got the value, I got the ZC value 547. 547.72. Okay. 72 ohm. Now we already know beta L by 2. Beta L by 2 is, beta L value was 50.28 degree. So we can find out 10 beta L by 2. So this value comes out to be, and another thing. So this also we need to, find in per unit. So the base value is the characteristic impedance. Okay. So even if you don't find the ZC value, that is also okay because we need to find the per unit value. So that is simply half tan beta L by 2. Beta L by 2. Okay. So I got the value 0.2346. 2346 per unit. Okay. So beta L here is equal to 50.28 degree. Fine. So this is what I got. So the correct option is option A, 0.235 per unit. Okay, let's proceed to the next question. Determine the SVC susceptance at maximum var absorption limit delta equal to 40 degree if the slope of the control characteristic is 0 per unit. So in the beginning of the question, it was mentioned that the limit of delta is 40 degree to 90 degree. So obviously the maximum absorption will be at delta equal to 40 degree. And the maximum production will be at delta equal to 90 degree. Okay. So what is the SVC susceptance when the control characteristic, the slope of the control characteristic is 0 per unit? What does that mean? What is the control characteristic and what is its slope? Let's look into that. See, so we talked about the uh, reactive power compensation that is performed by SVC, right? So we already saw this characteristic. Okay, this is called the control characteristic where the x-axis is ISVC, the current of the SVC, and y-axis is the voltage of SVC. And this triangular portion, this and this was the conventional SVC characteristic that we already saw. So in this, in this positive side, this is the inductive compensation, and this side, this is the capacitive compensation. And these are the maximum limits. These are the maximum limits here and here. This is the maximum absorption limit, and this is the maximum production limit here. Okay. Now, if you see, this is the this line. This line is horizontal to the x-axis, so its slope is 0, right? But if we, instead of this zero slope line, if we just give a positive slope to this characteristic like this, so if we tilt this so that now it has a positive slope, right? We will get some advantages. What will be those advantages that we will discuss? But for now, so there could be zero slope where the line will be horizontal, uh, the line will be parallel to the horizontal axis, and we could also have the characteristic like this where there will be a positive, slight positive slope. Okay, slight positive slope. So in that case, what will change? What will change is, now if suppose this is the voltage V reference, this is the voltage V reference. Now what will be the voltage? The voltage will be, the SVC voltage will be V reference plus ISVC excess, where excess is the slope. The slope is excess. Okay. In that case, the VSVC will be this. And if the slope is 0, then V reference is equal to VSVC. Right? In the question, they are asking what is the SVC susceptance if the control characteristic slope is 0. So we just saw that VSVC is equal to V reference when the slope is 0. VSVC is equal to V reference. Okay. V reference. And what is the relation between VSVC and ISVC? ISVC is equal to minus PSVC and VSVC. What is BSVC? BSVC is the susceptance. This we need to find out. BSVC. Okay. Okay. So just we will go step by step. So earlier, if you remember, we wrote one relation. What was the relation? So VSVC, when we were discussing the Thevenin equivalent circuit, we wrote VSVC is equal to V Thevenin minus XTH ISVC, right? From by applying KVL in the Thevenin loop. Okay. And here we are getting another relation, which is VSVC is equal to, from the control characteristic, we are writing this, is equal to Vref plus XS ISVC. We just saw this, right, from the control characteristic. So this from this one. So this is the slope, and VSVC is V reference plus ISVC times XS. Okay. If you just look at these two equations, you can compare this, right? From both these equations, you can find out what is ISVC, right? Or you can just compare this like this. So this will be, both are the expressions of VSVC. So VTH minus XTH ISVC is equal to VREF plus XS ISVC. From these two equations, you will get what is ISVC. ISVC is VTH minus V reference, VTH minus V reference by XTH plus XS. Okay. XTH plus XS. When the slope of the control characteristic is 0, then XS is equal to 0. Okay. So here XS is equal to 0 because the slope is 0. XS is equal to 0. What is V reference? V reference we already found out. What we take as V reference? V reference is the voltage that we got at rated load. V reference is Vm at rated load. That means when delta equal to 60 degree, that we solved in the first question. Okay. At delta equal to 60 degree. That we already found out. That was 0.957 per unit. Okay. 957 per unit. And we also need to find out what is V Thevenin when delta is equal to 40 degree. Okay. Because in the question they have asked to find it out when delta is equal to 40 degree. So again we will find out what is. So this is cos delta by 2. Delta by 2. Just a second. So cos delta by 2 by cos beta L by 2. So delta is 40 degree. This is cos 20 degree. Cos 20 degree by cos 25.14 degree. Because beta L value was 50.28 degree. So beta L by 2 is 25.14 degree. This comes out to be 1.038 per unit. 038 per unit. Okay. Now it is simple. You need to find out what is ISBC. So ISBC you can find out from that expression is equal to VTH minus Vref by XTH. XTH will remain same and XS is 0 here. So this is 0. So ISBC is equal to 0.3446. Okay. 3446. Then what is VSBC? VSBC is equal to minus ISBC by VSBC. VSBC by VSBC. Okay. When XS is equal to 0, VSBC is equal to Vref. Okay. So this comes out to be, so VSBC is 0.957 and this is ISBC. So this is minus 0.360 per unit. Okay. Per unit. The right answer is option D. Okay. Yeah, so I will take a short break, 10 minutes, then I shall resume the problems. Okay. So let's see the fifth question. So in the last question, the it was asked to calculate the SVC susceptance when the slope is 0. Now it is asked to calculate the susceptance when the slope of the control characteristic is 0.05 per unit. That means there is a 5% slope, positive slope. In that case, what will be the susceptance? So we will use the same equations, just the difference is that now xs is not 0. Now xs is not 0, it is 0.05, right? Now it is 0.05. So V Thevenin remains the same. V reference also remains the same. So now the current will now be point 0.284 per unit. Okay. This is excess is now this is 0.05. Now you will have to take care that now VSVC also changes. Why? Now VSVC is equal to V reference plus excess times ISVC. Earlier it was VSVC was equal to V reference because the slope was 0. V reference we already calculated 0.957, and excess is 0.05. ISVC we just calculated 0.284, right? 0.284. So now the new value of VSVC is 0.971. 971. Now this is not the value. Now VSVC is minus 0.292. 292. Okay. So the correct option is option A. This is the correct option. Let's see the next question. Determine the SVC susceptance at maximum var production limit. Earlier it was at maximum absorption limit. Now it is at maximum production limit. That means the SVC is operating in capacitive mode. Delta equal to 90 degree if the slope of the control characteristic is 0. Right. So now the only thing that will change, that changes is the delta value. So now we will put here as delta is equal to 90 degree, here it will be cos 45 degree. This is cos 45 degree. Okay. So now the Thevenin will change. What will be the new Thevenin? Thevenin is 0.7811 per unit. Okay. 811. Xs is 0 in this case. So we will just have to do the math. Thevenin we calculated, V reference remains the same. V reference doesn't change. It is 0.957 and XTH is also same 0.235 per unit. So ISVC is minus 0.7485 per unit. 7485. Right. And what is VSVC here? VSVC is equal to V reference. Okay. So now VSVC is equal to V reference because XS is equal to 0. Now the susceptance value will be, so this is ISVC and VSVC is equal to V reference equal to 0.957. So BSVC value is 0.782. 0.782 per unit. Option C is correct. Again, the next question is same, except now the slope is 0.05 per unit. So this is very easy. Just what you need to change, the changed value will be, so ISVC will obviously change now. ISVC will change because you will have to put X is equal to 0.05. So with the new value, this 0.617 per unit. 0.617. And VSVC also changes. Now, what is VSVC? Its value is 0.926. 0.926. And BSVC comes out to be point. So here the correct option is option B. So we just saw four different cases. One is this limit where delta was equal to 40 degree, which was when the reactive power was getting absorbed. Inductive compensation. For this case, another one for delta equal to 90 degree, which is capacitive compensation. Now for these two cases, we considered Xs equal to 0 and Xs is equal to 0.05, right? So when there is no slope, when the slope is 0, equal to 0, and when there is a positive slope, X is equal to 0.05. And similarly for delta equal to 90 degree, right? Let's see the next question. Determine the maximum power flow of SVC compensated line if the slope of the control characteristic is 0 per unit. So now the power flow in the SVC compensated line needs to be calculated. So the power flow expression changes when there is compensation, right? That we already know. And what is the expression? The expression is VSVC by ZC sine beta L. This is for a long line. ZC sine beta L by 2 sine delta by 2. This is the expression. Now VSVC will change depending on whether there is a slope or the slope is 0 or there is a positive slope, right? Depending on that, VSVC will change. The other things will remain constant, ZC sine beta L by 2, and also delta will change. Here they have asked maximum power flow. So whenever we are talking about maximum power flow, so obviously delta is equal to 90° for maximum power flow, right? So delta is equal to 90° here. Okay. Yeah. So after we just replace the expression of VSVC by this, so this we found out, right? So this expression, so you will get two parts. You will get two parts, right? Like this. So like this we can write, and there one variable is introduced k, small k. What is small k? Small k is this quantity xth by xs plus xth, and 1 minus k, this is 1 minus k, and k is equal to this is k. Okay, so this is the whole expression of PSVC. So let's just solve this. So we need to find out PSVC at delta equal to 90°, right? PSVC, that is PSVC sine delta by 2 sine delta by 2 by sine beta L by 2, and here it is ZC, right? It is ZC. So we need to find out the per unit power, right? So we will just divide each voltage by the base voltage. So this is V by V base, and then VSVC, VSVC by V base, then sine delta by 2. In the denominator also, here we can place VB square, VB square sine beta L by 2. So this quantity here, ZC by VB square, this is 1 by PC, where PC is the surge impedance loading. So what will be the per unit power? P SVC per unit is P SVC per unit is equal to this. Suppose this is sending end voltage. So PS per unit. We just converted everything in per unit. That's it. VSVC per unit. Then here sine beta L by 2. Beta L by 2. And here sine delta by 2. Right. Sine delta by 2. So this sending end voltage per unit value, we can take 1 per unit. And what is VSVC per unit? That is equal to Vref. Because now the slope of the control characteristic is 0. So 0.957 and then sine 45 degree. Sine 45 degree is 1 by root 2. That is 0.707. 0.707 and here sine beta L by 2 is sine 25.14 degree. 14 degree, right? So this comes out to be, as per my calculation, 1.592. 1.592 per unit. So the correct option is option C. Okay. We have similar question with the difference that now excess is 0.05 per unit. Just like we calculated the susceptance, here also we will have to make the necessary changes so that we can consider this excess value. Okay. So the only thing that will change is VSVC per unit here. So now VSVC per unit will be Vref plus ISVC. So now VSVC will be equal to Vref plus ISVC excess, right? ISVC excess. How we will calculate ISVC? We already have calculated this. So you will have to find out V Thevenin at delta equal to 45 degree. And rest of the values we already know. Okay. So V Thevenin, we can calculate. Okay. What is V Thevenin? So cos 45 divided by cos beta L by 2. Okay. So that is 0.7811 7811 minus 0.957 957 5.235 plus 0.05 0.05. Okay, equal to this is minus 0.617 and now we can calculate TSVC. This is equal to 0.926. 0.926. Right. So now you just replace these values over here. So this is 0.926. 926. The rest of the things will remain same. So this is the value is with a positive slope of the control characteristic, the power changes. The power flow changes. Now it is 1.541. Earlier it was 1.593. Now it is 1.541. It has changed. Okay. Okay. So the 10th question, this is a theoretical question. Which of the following is the voltage across SVC in Thevenin equivalent circuit? So the four options are given. You will have to find what is the correct expression of VSVC. Okay, so we can easily find that out. VSVC was from the Thevenin equivalent circuit. It was VTH minus XTH ISVC. And now you will have to write the expression for ISVC. First XTH. What is ISVC? That is V Thevenin V Thevenin minus V reference. Minus V reference, right? Minus V reference by XTH plus XS. XTH plus XS. Okay. So if you just calculate this, if you simplify this expression, you will get option B is the correct expression. Okay. So option B is the correct expression. The next question, which of the following statements is true? So SVC with positive slope of control characteristics has the capability to mitigate overvoltage and undervoltage in a wider range of system operation compared to zero slope control characteristics. Next option is SVC with positive slope has the capability to mitigate overvoltage and undervoltage in a lower range compared to zero slope control characteristic. So the first option is saying that if you have a positive slope instead of zero slope, then you can mitigate the overvoltage and undervoltage in a wider range. And the second option is telling that you will not get a wider range, the range will be narrower. The third option is SVC with positive slope of control characteristic has the capability to mitigate only under voltage. And the last option is has the capability to mitigate only over voltage when the slope is positive. So to find the correct answer, we will have to look into the control characteristic along with the load lines, right? Along with the load lines. So these red dotted lines, they are the load lines. These red dotted lines, at which point they intersect this characteristic, at that point we will have to take. So if you just look at it carefully, this black line, this is the line with zero slope. And this red line is at the extreme positions, the red line is cutting it here at this point. So this is the extreme limit. And here in the capacitive compensation, this is the extreme limit, right? When there is zero slope. But when there is positive slope, you see this same load line, which is cutting it here, it is cutting the positive slope line here. You see, you have to provide lesser compensation compared to the zero slope line because it is decreasing. It is cutting it here, but it is cutting this green line here. So the amount of compensation reduces. So you see your area, you can compensate it for wider range. You can compensate it for wider range. So this much is the extra range you get. This much here and this much here. So this is the extra range you get if you provide a positive slope. So the correct option will be option A. Okay, this is the correct option. So I hope you understood the problems. If you have any doubt, you can ask me in the next class. So thank you for joining, and we will meet in the next week. Thank you.